Hola! Bienvenido a Collab. Now, Tom Husband's going to show you a chemical magic trick for turning milk into toffee. Enjoy!
Good evening. In the early 1970s, British ingenuity transformed a field in which we were already established world leaders. It was a creation that revolutionized the world of comestible technology. I refer, of course, to the Banoffee pie. Successor to the Blum's coffee toffee pie, this pucky pudding quickly established itself as a firm favorite in restaurants throughout the globe. It's easily recognized by its attractive aroma, but this delectable dessert is aromatic in more ways than one. Tom.
Thanks, Tom. Aromatic is a scientific word which has evolved beyond its original meaning. The first person to describe chemicals as aromatic was August Wilhelm von Hofmann, and although he was referring to their smell, the chemical meaning is now quite different. The toffee notes in Banoffee pie come from a family of compounds called maillard products. These tiny chemicals are aromatic in the true chemical sense and the fragrance sense. And I'll show this with some chemical kitchen wizardry. I'm going to make toffee by heating this tin of milk. I'm going to heat the tin for about 2 hours, and when I open it you'll see that the milk has transformed into a gooey brown toffee, more accurately described as caramel. You may be wondering, since when does heating milk make caramel? Milk contains sugars and proteins, which are themselves formed from amino acids. Under heat, the sulfur and nitrogen atoms from the amino acids join with carbon, hydrogen and oxygen atoms from the sugars to form the maillard compounds, and crucially, they form the ring structures at the heart of the chemicals that make them chemically aromatic. So, are all molecules with ring structures aromatic? Not at all. Even the sugars in the milk we started with contain 2 rings, and they're not aromatic. It takes a certain sort of electron sharing within the ring structure to be truly aromatic, and nowhere is this better illustrated than in the king of aromatic compounds, benzene. Benzene's structure puzzled scientists for many years. A major breakthrough was the realization that the compound must be looped, or cyclic, but this still didn't explain benzene's bonding. The proportion of carbon and hydrogen atoms suggested that each molecule should feature alternating single and double bonds, but this clashed with X-ray crystallography data, which showed that all the bonds had the same length. The only way to reconcile this conflict is through our modern understanding of aromaticity. The outer electron shell of a carbon atom can be subdivided into 1 s orbital and 3 p orbitals. In each of the benzene ring's 6 carbon atoms, 1 s orbital merges with 2 p orbitals to form 3 sp2 hybrid orbitals. The electrons in these hybrid orbitals form a kind of covalent bond called a sigma bond. This means that each carbon atom has 1 electron and 1 p orbital left over. What happens next is these p orbitals merge together to form a pi cloud hovering above and below the ring structure, which is occupied by all the leftover electrons. These electrons are not associated with any particular atom and can roam free throughout the pi cloud. They've become delocalized. And this is the defining characteristic of an aromatic compound, a cyclic structure with this conjugated pi system, a series of bonds which are stronger than single bonds, but weaker than double bonds, and equal in length. Maillard compounds are also aromatic in this chemical sense. There are 8 families of Maillard compounds, all of which are arranged around a central aromatic ring. Unlike in benzene, these rings are not formed purely from carbon atoms, but contain nitrogen, oxygen or sulfur atoms. But these ring compounds still contain parallel p orbitals which merge to form pi clouds of delocalized electrons, a cyclic conjugated pi system. These rings feature a multitude of offshoots called side chains, which are not shown in the diagrams. Hundreds of thousands of slightly different compounds are formed whenever these reactions occur, contributing to the richness of their collective smell. They're responsible for the fragrance of toast, the aroma of coffee, the whiff of chocolate, and the sumptuous scent of barbecued meat. And that explains how heating a tin of milk can transform it into caramel, which can be added to the crushed biscuit base, slices of fresh banana, and whipped cream
to make a sumptuous Banoffee pie. Tom.
Thanks, Tom. But don't forget, the most important ingredient in Banoffee pie is pie. Clouds of electrons in the compounds.
He's so good. But he is new talent, so we'd love to get your feedback on him. So tell us what you think down below and subscribe. Bye.